Yeah. So this week we'll be finally entering the topics and discussing fluid dynamics. And so this lecture will end with basically Navier-Stokes equation this week. So till now we have been discussing kinematics, where we were discussing about velocity gradient tensors and what kind of flows there will be, or how can we characterize the flows, or what can we talk about the nature of the flows from looking at how the velocity field changes as a function of x, y, and z. Until now, we have not been talking about what causes velocity gradients, or what are the kind of forces acting on the fluid, mm, which can cause velocity gradients. On the other hand, we can also discuss about if one has certain velocity gradients, what would be the kind of nature of the forces or the stresses which will be acting on a fluid element. So we're going to start with that, properties of the stress tensor, then correlate or write the stress tensor in terms of the velocity gradient, the shear rate tensor. Um, for simple fluids, and we'll talk about what are the approximations, and finally uh, write down the Navier-Stokes equation, which is essentially a Newton's equation adapted for that of fluid, so that you have velocity changing as a function, explicitly a function of time, as well as xyz, because you can have effective flows. So this is what the plan of this week's lecture is. Meanwhile, going into the details, to start off, just to repeat, fluid dynamics is discussion about forces and the strain rates produced by as a consequence of forces acting on fluid. So first we discuss about fluid at rest, and suppose this is a certain area, uh, surface area within the fluid. We've divided the fluid into two parts, lying to the left of the surface area in this black color, which we call fluid element 2, which acts and gives a force mm, uh, on the right side of the surface, which we call fluid element 1. So this force which is acting has origins because molecules are moving and colliding against the molecules which are on the right hand side of the surface, and that creates a certain hydrostatic pressure. So fluid element 1 gives hydrostatic pressure to fluid 2, and fluid 2 in turn gives some hydrostatic pressure on fluid 1. So when you're looking at fluid 1, the amount of force which is acting in on the fluid 1 by fluid 2 acts in this direction, and when you are focused on fluid element 1, the outward surface normal will be in this direction, right? So the pressure, if you write in terms, so if you talk about the force acting, it is opposite. There's a force acting on fluid element 1 is opposite in direction to the outwards normal to the surface. And if there's a force acting on the surface area, the stress will be the total force acting, pressure act, force acting per unit area, and that's the pressure. And if the fluid is at rest, this force acting, or the pressure, hydrostatic pressure, and uh, this acts is isotropic, is the same in all different directions, and independent of the orientation of dA. So the force acting on in any direction, and this can be oriented in any direction. Of course, it's a small element located at any point, and this can be oriented in any direction. And as long as fluid is at rest, there's the same fluid force acting across a surface area, which we call the hydrostatic pressure. If there is fluid in motion, there will be additional tangential forces between layers of fluid having relative velocity with respect to each other. If the fluid element was uh, if there was an amount of fluid and it was moving as a whole in uniform velocity, where different parts of the fluid were not moving with respect to each other, but the whole center of mass had uh, finite velocity, then you would essentially could change the reference frame, and you essentially have again fluid at rest. However, if different parts of the fluid are moving, have a relative velocity with respect to each other, then if you take a small fluid element and look at the surfaces, you would have viscous forces acting, because there are fluid elements moving with respect to each other. So if a fast moving fluid will be slowed down, uh, the fast moving fluid across a surface will be pulled back and slowed down by the slow moving fluid, and the in turn the fast moving fluid will try to pull and increase the speed of the um slow moving fluid. So there will be viscous forces. What do viscous forces do? And viscous forces act on the surface of the fluid. It transports momentum from a region of high momentum density to a region of low momentum density. And this high momentum density, momentum being a vector, you can have three different components of the vector: px, py, pz. And across the surface, and the surface can be oriented along ax, ay, az, or any combinations of these two. So this px, py, pz, each component of momentum can be transported because of viscous forces. Uh, so momentum transport can happen along any direction. So py can be transported across uh, d daz, suppose, and px can be transported across a surface element which whose normal acts along the y direction. So there can be different. So the basically what you have is forces acting in different directions, ijk, acting on surface areas which can be pointed around any direction, and hence uh, the stress you can have fx, force in the x direction, acting across an area pointing in the y direction. As a consequence, the stress will have an is a 9-component tensor. So basically, stress will have uh, this I runs from 1 to 3 xyz, and dA, area, element of the area, runs from xyz. So basically what you will have, stress tensor sigma ij can have sigma xx, sigma xy, sigma xz. And what does sigma xx mean? It means that force, so sigma ij xx, force is acting in the ith direction, which is acting across surface whose normal is along the j direction. So force along x direction acting across a surface whose normal is in the y direction. Forces are in the x direction acting across a surface whose normal is in the z direction. Here I would like to point out Here I would like to point out that, by the way, this what I said is the convention of physical hydrodynamics by the 4 authors, whereas the Kundu and the 3 authors use a different convention to define the stress tensor, and what they use is that on surface AI. So the first index is on surface AI force J acts. Since you will be referring to both the books, I highlight that these two books have different conventions to define stress tensor. But as you shall soon see, that sigma ij is equal to sigma gi for a large class of systems, for most systems, in fact, wherever angular momentum, yeah, so we'll talk about it. And so it won't matter. But anyway, the conventions followed in these two books are different. And for simple fluids, where you can make a very general approximations that molecules are not rod-like or chiral, there are no magnetic fields, you don't have basically charged particles which are moving in magnetic fields, and one has forces, body forces. What is a body force? Is basically a force which is acting on each element, on the fluid, in the whole of the fluid, on each atom of the fluid, atom or molecule of the fluid, and not only at the surfaces. Viscous forces act only at the surfaces. So gravity, it is acting on the entire element of the fluid and not across surfaces. Each part of the fluid feels the same force, gravitational force. So those, so suppose one has forces which are conservative, there are no density gradients uh, due to, suppose, changes in temperature, the entire fluid is in uniform temperature or pressure. Then uh, the viscous forces which create deformation. Okay, so we'll be discussing those forces which are related to the symmetric part of the stress tensor. So it's experimentally seen that the forces which cause deformation are related to the symmetric part of the velocity gradient tensor. And just to remind you, any del Vx del y can be written as, or can be rewritten as, the symmetric part and the antisymmetric part. And we saw in the past that the symmetric part of the velocity gradient tensor is the part which causes pure deformation without any rotation, whereas the antisymmetric part causes rotation without deformation, right? So we are going to relate the viscous forces to the symmetric part of the stress tensor. The next thing to show is that sigma ij equal to sigma ji. So these conventions are not going to matter. And since we are talking about forces which are related, uh, which will be shown to be related to this only symmetric part of the of the velocity gradient tensor. So the viscous forces do uh, do depend upon the symmetric part of the force tensor, and hence these forces uh, do not cause any rigid body rotation. Okay, so these forces do not, so viscous forces do not provide torque to the entire element of the fluid. They do not cause rigid body rotation unless you have a fluid consisting of ferromagnetic particles, and there are some magnetic fields which can cause these ferromagnetic particles to rotate, and locally there will be generation of angular momentum. So we are not considering such cases. And suppose you have a fluid element, this cubic, a small fluid element, uh, and within the fluid element there is no net acceleration. So it's either in a steady state, so the fluid element is in steady state, so that there are no net forces acting on it. Then some net forces acting on this fluid element, it would accelerate. Um, right? So that's not the case. You can have a steady state system, or and locally, suppose along the surface, suppose this is the x direction and this is the y direction. So if this is the x direction, right, so then this would be dx along the x direction, this is dy, and then this would be dz. Now suppose fy, a force in the y direction, was acting across the surface area whose outward normal is in the x direction, then sigma y, because force in the y direction, the first index is the direction of the force as per the conventions of physical hydrodynamics, acting on the x direction, the stress tensor would be Fy by dAx. And similarly, there is a force which is acting in the minus y direction, equal and opposite to this. Why? Because we are saying that we are considering at the moment uh, a fluid element which is not accelerating. If there was a net force, then this entire thing would accelerate or advect. Right? So we are not considering that. So the amount, so this element of fluid, the center of mass is not moving. The total amount of force acting in any particular direction is the same, but there is here on this surface area, there is a in the positive y direction, and there's a negative y force acting in the negative y direction on this, and the total in that case, the total uh, torque acting on this fluid and these two surfaces would be the sigma yx into the area would give the force. So what would be the area? Dy into dz is the total area of dax. Normal is in the x direction. And these two forces are separated by distance dx. So the torque on this will be sigma y dy dz dx. And exactly we can do something similar on the surface area. Suppose there was a force acting in the x dash direction, in the x direction on the surface area, which is pointing, which is an outward normal in the y direction, then the total uh, force acting on this surface is fx dash into dx into dz, right? Sigma xy into dx into dz. So, and if there's a force acting in this direction for the center of mass of the fluid not to move, there would be equal and opposite force acting, I mean, stress tensor, if you like, acting in this direction, and the total torque, and which is coming, and the total torque, and this is the viscous torque, which is related to the symmetric part of the stress tensor, which I said does not cause any center of rigid body rotation. So, so this is the torque acting in this x direction. So as a consequence, the total torque has to be 0 and this has to be equal to 0. The consequence of which you can see that sigma yx equal to sigma xy, right? So it's a consequence of that these forces cannot apply a net torque to the element of the fluid, because the stress tensor is related or will be related to the symmetric part of the velocity gradient tensor, which does not cause any rigid body rotation. Hence, there can be no torque into the system. So this is often explained in the books by using the terms of equilibrium of torques, net angular momentum conservation, balance of torques, so that there is no net rotation as a rigid body, but its physical content is what I said. And the consequence is that sigma xy equal to sigma yx, which means fx by ay per unit area is equal to Fy by Ax. If if this did not hold true, if this relation did not hold true, there would be rigid body rotation. And as I said, as I've repeated many times, viscous forces are related to the symmetric part of the stress tensor, which in general can be written as essentially Eij half del Vi del Xj plus del Vj del Xi. So this is symmetric. If you change ing, it will uh, right. So that's basically what the content of the slide is. Here again I have defined what is sigma xx fxx. So if you had a symmetric part, you would have fx acting on ax, and the shear part in the fxy means force fx acting on ay, right? So that's what the content is. Now, what I want to say, that if there was so basically the stress tensor sigma ij can be broken up into two parts. One part which is caused because of the velocity gradients, relative velocity in different parts of the, between different layers of the fluid, as measured by the strain in the fluid, or the rather the strain rate, because it's a fluid, it will have strain rate and velocity gradients. And this part uh, acts only when there is relative velocity, and is related to the and is also called the viscosity stress tensor. And this part, the forces which are defined by this part, causes deformation of fluid element, and you could have volume deformation or shear deformation, right? And yeah, and if sigma ij is uniform as a function of xyz, then it does not cause net flow. And since this is also related to the symmetric part of the velocity gradient tensor, it does not cause any rotation. On the other hand, when fluid is at rest, uniform translation, there's another isotropic part of the stress tensor, which exists even in the absence of velocity gradients. And in the absence of velocity gradients, we identify this quantity with the thermodynamic pressure. However, if the fluid is in motion, we cannot, uh, the thermodynamic pressure is defined only for equilibrium when there are no currents. So then we cannot identify it with the thermodynamic pressure, and instead identify it with some mean mechanical pressure. So in general, this part which causes motion, this part is denoted by a dash, and the total stress tensor, which includes uh, pressure, whether it's mechanical or thermodynamic, I'm not specifying, but pressure, which is there only, which contributes only to the diagonal components of the stress tensor, right? This has both diagonal and off diagonal terms, as we said. See, so this is contributing only to the diagonal parts, and this with a dash, the viscosity stress tensor can be written as. Now, I remind you that the velocity gradient tensor, right, had a part, so which contributed to volume change, which is the diagonal parts. Uh, So, and it could be written down in the velocity gradient tensor could be written in a way so that this part, the so-called deviatoric part of the velocity gradient tensor, was associated with velocity gradients which did not contribute to volume changes. So if you sum up, if you took the trace, or you summed up the diagonal elements which contribute to the velocity, to the volume change for this uh, part, the sum of the diagonal elements equal to 0. So this part is not related to the velocity change. This can be written as the stress tensor. The viscosity stress tensor has a coefficient which is called bulk viscosity, which is related to dilatation, or dilation is also called dilatation. So, but we'll just use the word dilation, associated with the volume change part and a viscosity term. So this is bulk viscosity and this is shear viscosity term, which and this does not contribute to the volume change. Though it does not contribute to the volume change is basically the sum of the diagonal parts. So this part does not contribute to the volume change, but you can have stresses and forces along coming from this part. So forces acting in the x direction across surface areas whose normal is in the x direction, or forces coming from this part acting in the y direction across surface area, or acting on surface area which is pointing in the y direction, whose normal to the surfaces along the y direction. But these forces will act in such a way so that this the stress rising from this will not lead to any volume change. The other thing to is note that here there is repeated index, which means that it's more like, if you remember what, so basically sigma, eij is half of del vx del y plus del vy del x. But if you have a repeated index, remember it will be more like a divergence of v term, right? Because you will have a del vx del x plus del vx del x, right? So there will be a factor of 2 coming here from eij, and that will cancel out this half. So if you're just writing in terms of eij, and there's a repeated index, so del vx del x, del vy del y, del vz del vz, del z. So that's like divergence vx. So that gives, at a certain point, the mean deformation acting along the, the contribution of deformation which is perpendicular to the area. And the diagonal term, if so, okay, so let's look at, yeah, so sigma dash xx, sigma dash xx will have a zeta, the bulk viscosity, into divergence v, this is because of the repeated index, and then 2 eta del vx dx minus 2/3 eta divergence of v, right? So that's what you will get uh, from this term. So note there's a 2 here, so hence you will get, right? So basically this is characterizing the mean deformation along the same direction along which the force is acting. But this will contribute, there will be a non-zero term. Suppose yeah, so this will contribute if along a particular direction the deformation is more compared to the mean deformation coming from divergence v. And this is very nicely explained in Kundu on page 97. So you're not only looking at the mean deformation, but excess deformation along one particular direction beyond the average. And then it will appear with the shear viscosity term, right? In general, here I just wrote down the equation, but I want to highlight that sigma ij is a tensor, so it's a force acting in I direction, um, acting on surface area whose normal is in the j direction, and this EIKL, the deformation tensor, is also a tensor, right? So deformations in, or the gradient of deformations along particular directions in general can cause stresses in any arbitrary stress co- components in any arbitrary direction. So in general, these two tensors will be related by this, which has four indices, right? Uh, because velocity gradient in any particular direction can cause a stress in any other, I mean, in direction, I mean, which has two other components. That would be in general, I mean, the properties of tensors. If this depends on this, there will be four indices here. But based on experimental validation, right, one knows that liquids like water are isotropic. The stress tensor is isotropic and symmetric. In different directions, the stress tensor does not vary. On the other hand, if you had molecular fluids uh, where suppose all the molecules were pointing in the same direction on an average, then uh, the viscosity, I mean the response of pulling an object through the fluid in different directions would be different. So if you had molecules which were all pointing along the same direction and you tried to have a relative velocity in this direction, right, uh, whatever would be the forces, because you're relating forces to strains, or rather strain rates. So the forces which would be acting when uh, molecules slide past each other versus if they had to move in this direction would be very different. So the fluid would not be isotropic. So, but many fluids, especially from our daily experience, especially water, the stress tensor is isotropic and there is no angular momentum which is created within the fluid by virtue of its flow or by virtue of external fields. So sigma xy equal to sigma yx, and that these assumptions essentially are based on years of experimental validation. Now, if one has a fluid which is isotropic and symmetric using some very simple tensor algebra on which I don't want to focus about, because I want to focus on the physical idea. And finally, those tensor uh, algebra you are able to do based on these assumptions. And what I want to highlight is that these assumptions come from experimental validation and not from mathematics. What you see is the stress tensor, viscosity stress tensor, can be written in terms of velocity gradients where there are only two independent coefficients instead of, you know, this this fourth rank tensor. So all of them are not independent of each other, and finally there are only two independent things. And usually for fluids, with cases like that of water, you see that the contribution which comes due to volume change is often pretty negligible. So the sigma dash viscosity stress tensor primarily depends upon a single coefficient called the viscosity of the fluid, and the stress tensor is dependent on the symmetric part of the velocity gradient tensor in particular, uh, which is not dependent on which does not contribute to volume change as it flows. But yes, if the fluid is compressible and if there are very rapid density changes, rapid in terms of XYZ and time, then this can also start to contribute. In general, this is the bulk viscosity, which is associated with volume change of an fluid element. This is the shear viscosity, which is related to relative velocity between different elements of the fluid which flows past each other, right? uh, yes, so that's what I want to say. The off diagonal terms, if you wanted to look at the off diagonal terms, they are simpler. One can write sigma ij, the sigma dash, the viscosity stress tensor. In addition, there's the so-called pressure term, sigma dash xy equal to eta, and this assumes that there is uh, only one coefficient. It assumes that viscosity is same in all directions. You have Newtonian isotropic fluids, and this is also called the first coefficient of viscosity. The stress tensor depends upon the first coefficient of viscosity. This is the same in different directions, and it is related to the del Vx del y del Vy del x. And if you had, suppose, Zy, the stress tensor in the y, so first of all, stress dash sigma dash yz will be equal to zy, and again that can be related to um, del Vx, so del Vz del y and del Vy del z. Here there is no, so note, there is no half factor, because the way this was written, it was written 2 into eta, right? Eij has a half factor, but this 2 and that half factor cancels. So basically what you have is the velocity gradient. And this again, I mean, suppose you had layers of fluid flowing in the x direction, and there was a velocity gradient in the y direction. On the other hand, there was no velocity gradient. I mean, del Vy del x was 0. This is basically this case that we have always, then we get back our familiar expression of sigma dash xy viscosity stress tensor is equal to eta into del Vx del y. That's what you have already seen, or we have already discussed in the past. Uh, okay, so this part I will again record as part 2 of the lecture.